In this video, we're going to discuss the comparison test for series, which will be used to determine the convergence or divergence of a series by comparing it to a series whose convergence or divergence is already known. In order to use the comparison test, we're going to need a collection of series whose convergence or divergence is easily determined, in which to compare to. And fortunately, we have already talked about two such classes of series. We have the geometric series, which are a series that can be written in the form sum n equal 1 to infinity of a times r to the n minus 1. And we have previously seen that geometric series will converge when the ratio r is less than 1 in absolute value, so when the absolute value of r is less than 1, and that the geometric series will diverge when the absolute value of r is greater than or equal to 1. We've also have the p series, the sum n equal 1 to infinity of 1 over n to the p, and we've seen that these series converge when p is greater than 1 and diverge when p is less than or equal to 1. When we use the comparison test, these will be the two types of series that we will typically compare to, because we can determine convergence or divergence simply by looking at the form of the terms in the series. To get an understanding of how the comparison test works, let's start by considering the series the sum n equal 1 to infinity of 1 over n squared plus 1. This series looks similar to the series n equal 1 to infinity of 1 over n squared, the only difference being that the terms of the first series will have a denominator which is one more than the terms in the second series. The benefit of looking at this second series is that this is actually a convergent p series. We can see this just by looking at it without doing any additional work. Here, this is a p series where p is 2, and 2 is bigger than 1, and so we know right away that the second series is convergent. And so the first series looks very similar to this one, and so we might think that it's going to converge as well. To make this a bit more formal, we can write out the first few terms of each of these series and compare the terms, the corresponding terms between the series. If we look at the first term, for example, in our original series, we have the first term of 1/2. And for the compared series, we have the first term of 1. And certainly we know that 1/2 is smaller than 1. And so this is a sideways less than sign, indicating that 1/2 is less than 1. And if we move and look at each subsequent term, if we look, for example, at the second terms, we see that 1/5 is less than 1/4. 1/10 is less than 1/9, and 1/17 is less than 1/16. And if we wanted, we could certainly continue this by comparing the fifth term and the sixth term and the seventh term, or more generally, we could compare just the general nth term. And we can see here that 1 over n squared plus 1, the nth term of our first series, will always be less than 1 over n squared, which is the nth term of our second series, because it has a larger denominator. That plus 1 in the denominator of our first term will always make that term smaller than 1 over n squared. We also know that this will be greater than 0, since n squared plus 1 is always going to be a positive number when n is a positive number itself. Now, this inequality relates the nth term to each of our series to each other. And we could extend this inequality to the partial sums for each of our two series and see that any partial sum for our first series will always be less than the partial sum for the second series. We can then take limits of those partial sums, and we can see that the limit of the partial sums of the first series will be smaller than the limit of the partial sums for the second series. And since limits of partial sums are the values of our series, what we obtain here is the inequality that 0 is going to be less than the sum n equal 1 to infinity of 1 over n squared plus 1. This was the series that we're looking to determine the convergence for. So we know that series is going to be something bigger than 0. And we also know it's going to be smaller than n equal 1 to infinity of 1 over n squared. And again, that is because each of the terms of the first series are smaller than the second, and therefore each of the partial sums of the first series will be smaller than the partial sums of the second, and therefore the limit of the partial sums of the first will be smaller than the limit of the partial sums of the second. And that's exactly what we have written here. And now the important part, as we mentioned before, this is a convergent series because it's 1 over n squared, and 2 is bigger than 1, which makes it a convergent p-series. And therefore we know that this sum is an actual number. It's not infinity. So we could say that that is strictly less than infinity. And now, by looking at this, we have no choice but to conclude that the given series that we want must also converge. What we see here is that it has a value that is bigger than 0 and less than infinity. And therefore, its value must be an actual number. This series cannot diverge to infinity because the series is smaller than 1, which converges. And it cannot converge to negative infinity because it's greater than 0. And so this series here, we know, has to converge to some number. Now, one important aspect here is that we do not know what it converges to. In fact, we do not even know what the sum 1 over n squared converges to. We just know that it does indeed converge to some number. And if we knew that number, this argument would tell us that 1 over n squared plus 1 would converge to a smaller number. But since we don't know anything about the values of the series, the most that we can say based on this calculation is that the sum n equal 1 to infinity of 1 over n squared plus 1 converges. As we will see in a few moments, the logic from this example extends to many other pairs of series. In particular, whenever we have two series where the terms of one are smaller than the terms of a second, and the second series converges, we'll always be able to conclude that the first series converges as well. So this will end up being 1/2 of our comparison test. Before we state the comparison test formally, we'll look at a similar example to this one, not quite in as much detail, to demonstrate the second part of the comparison test. To see the other side of the comparison test, let's consider the series n equal 1 to infinity of 1 over n minus 1/2. This looks pretty similar to the series n equal 1 to infinity of 1 over n. Just like in the previous example, these two series differ only by a constant being added or subtracted in the denominator. In this case, the sum of 1 over n is known to be a divergent p-series, because here p is equal to 1, and we know p-series are divergent when the value of p is greater than or equal to 1. And so here we see the similar series is actually divergent, unlike in the previous example where it was convergent. If we look to compare the terms of these series, what we notice here is that 1 over n is actually the smaller term. So 1 over n is always less than 1 over n minus 1/2. And that's because n is always greater than n minus 1/2. And so 1 over n has the larger denominator and therefore is the smaller number. We also know that 1 over n is greater than 0, so all of the terms here are positive. And so if we then extend the same logic that we did in the previous example, by looking at, we know that the nth term of each of the series are related in this way. We then know that the partial sums for each of the series are related similarly, as are the limits of the partial sums, which are the values of the series. And so what we obtain is that the sum n equal 1 to infinity of 1 over n is going to be smaller than n equal 1 to infinity of 1 over n minus 1/2. So we have the values of these series related in this particular way. Now we know that the sum n equal 1 to infinity of 1 over n is a divergent series. So we know this series here diverges. This is a divergent p-series. And so its value, when we take the limit of the partial sums, we get a value of infinity, since 1 over n is a positive term. That means that this sum here has to be greater than the value of the sum of 1 over n. And the only way for that to be possible is if this series diverges as well. If this sum had been a number, for example, let's say the sum of 1 over n minus 1/2 converged to 12, then what this would say is that 12 is actually larger than infinity, which we know is just absurd. And so anytime we have a series like this whose terms are larger than the terms in a divergent series, that given series must also diverge, or else we get something absurd, like 12 being greater than infinity. And so this is a way that we can determine whether a series diverges using by comparing it to another series like the series 1 over n here. So these two examples both indicate the idea behind the comparison test that we formally state here. So for the comparison test, we need to have two different series, so the sum n equal 1 to infinity of a sub n, and the sum n equal 1 to infinity of b sub n. And we need the terms of these series to be positive, and also one of the series terms to be larger than the other. So here we're going to assume that a sub n is always less than or equal to b sub n, at least eventually. So maybe there's a few terms at the beginning where this fails, but at some point this inequality is true from that point on forever. And so the two parts of the comparison test mimic the two examples that we've just seen. If the sum n equal 1 to infinity of b sub n converges, and b sub n here is the series with the larger terms, so if that series converges, then the sum n equal 1 to infinity of a sub n converges. And so in other words, if we have two series and the one with the bigger terms converge, the ones with the smaller terms must converge as well. The second part says that if the sum n equal 1 to infinity of a sub n diverges, that is the series with the smaller terms, then the sum n equal 1 to infinity of b sub n must also diverge, and that is the series with the larger terms. And so this mimics the second example that we saw before stating this test. Notice that to use either part of the comparison test, we do need to know ahead of time whether the series we're comparing to converges or diverges. And that's why it's useful to always compare to a p-series or a geometric series, since convergence or divergence of those series are easily determined. So to see a quick example of how to use the comparison test, let's consider the series n equal 1 to infinity of 1 over 2 to the n minus 1 plus n, and let's determine whether this series converges or diverges. The first thing that we're going to do is to observe that the term of this particular series, 1 over 2 to the n minus 1 plus n, is going to be always smaller than 1 over 2 to the n minus 1, because the larger denominator, forced by the plus n, is going to give us the smaller number. And so this is going to be true for all values of n. And 1 over 2 to the n minus 1 can be rewritten as 1/2 to the n minus 1. Right? Now, we know that the sum, n equal 1 to infinity, of 1/2 to the n minus 1, this is a geometric series, and this is going to converge because our ratio, which is 1/2, in absolute value, is less than 1. Right? And so what we have here is a series whose terms are smaller than the terms of a convergent series. And therefore, by the first part of the comparison test that we just stated, the sum n equal 1 to infinity of 1 over 2 to the n minus 1 plus n is going to converge by the comparison test. In this case, we compared it to a similar series, and the inequality was pointing in the correct direction. Our terms were smaller than the terms of a convergent series, and in that case, the comparison test tells us that we are guaranteed to have a convergent series.